Let's read the question. It's a trigonometry problem in 4 parts, an equation to solve and a graph to sketch, both built from the same expression. We're given an equation in theta over this range, and a function y made from cosine squared minus sine squared. And we must prove an identity, use it to solve the equation, sketch the graph, then find the range of h that gives exactly 8 solutions. So here's what we're working with: the equation and the function, and our goal of proving the identity, solving for theta, sketching the curve, and finding the range of h. Here's the idea that unlocks everything. This expression, cosine squared minus sine squared, is hiding inside both the equation and the function. It's exactly the double-angle form of cosine. Once we see it as cosine of 2 theta, every part becomes simple. Let's prove it first. Step 1. Prove the double-angle identity from scratch. Write 2 theta as theta plus theta, then apply the compound angle rule for cosine. Expanding the cosine of a sum, with both angles equal to theta, gives this. Each product is just that function squared, landing exactly on cosine squared minus sine squared. Proved. The rule behind that expansion is the compound angle formula. We keep it on the shelf. Step 2. Reshape the equation using our new identity. Here's the equation again. Bring the 3 signs squared over to the left. Both terms share a factor of 3, so factor it out. The bracket is exactly our identity, so it's cosine of 2 theta. Swap it in. Divide both sides by 3, and it collapses to cosine of 2 theta equals 2/3. Step 3. Solve for theta and mind the range. The equation is in 2 theta, so double the range. 2 theta runs from 360 up to 720 degrees. The reference angle is the inverse cosine of 2/3, about 48 degrees. Cosine is positive, so 2 theta sits in the all or cosine quadrants, the first and the fourth. In the first quadrant of this turn, that's 360 plus the reference, 408. In the fourth, it's 720 minus the reference, 671. Have each one, keeping full accuracy, and theta is about 204 or 336 degrees. Step 4. On to the graph. First, simplify the function with the same identity. Here's the function. Inside the bars sits our identity again, so it becomes minus the size of cosine of 2 theta, plus 4/5. First, how high and low does it go? Cosine stays between -1 and 1, the modulus floors it at 0. Flip it and lift by 4/5, and y runs from -1/5 to 4/5. Start with the basic wave, cosine of 2 theta. Over a full turn, it makes 2 complete waves, peaking at 1 and dipping to -1. Plot those key points first, then join them into a smooth curve. Now take the modulus. That flips every part below the axis up above it, so the dips become humps that just touch 1, and the curve never goes below 0. The minus sign flips the whole thing back down, so now it sits on or below the axis. Finally, add 4/5 to lift the whole curve up. The peaks land at 4/5 and the lowest points at -1/5. Every peak reaches 4/5, and the lowest points sit at -1/5. That gives 4 equal humps over a full turn. Peaks at the quarter pi marks, valleys at 0, pi over 2, pi, and so on. Part B2. We want the line y equals h to cross the graph exactly 8 times. Slide a line across at this height. It cuts each of the 4 humps twice, so 8 crossings. For all 8, the line must stay strictly between the bottom and the top. Right at 4/5, it would only touch the peaks, and at -1/5, it would meet 5 points. So h lies strictly between -1/5 and 4/5. Final answers. The identity is proved. Theta is about 204 or 336 degrees. The graph is 4 equal humps, peaking at 4/5 and dipping to -1/5. And h lies strictly between -1/5 and 4/5.